So I'll go ahead and make the project here. If I go build Flex HQ, we'll start it up. You can see we've got 8 threads that it allocated to our thread pool, each supporting 32 clients. I am seriously excited to bring this video to you guys today. You have absolutely no idea. Everybody and their grandma knows how to write a thread per client socket server, but today we are flipping the script. I've seen very few tutorials on YouTube of people writing Epoll servers where one thread can handle multiple clients at once in a scalable manner. And I've seen even fewer tutorials on YouTube where they use thread pools to balance load across multiple threads using that model. We're going to get into it today. It's going to be fantastic. Now, there are 2 things I want to mention real quick before we dive into the code. The first one is high-level architecture. Now, I know that you guys all want to jump into the code, but please don't skip the high-level architecture part, because when we actually write the code today, it'll give you an understanding of what we're trying to achieve with each part of the code we write, and you're not just copying and pasting exactly what I'm writing as we do it, because nobody learns anything that way, especially not you. The second thing that I want to discuss before we dive right in is the known quirks with the implementation we're going to be writing today. This is a 600-line piece of code, all right, that we're going to write in one video. There are things that I have left unfixed for the sake of brevity. So before you waste a bunch of time writing an essay in the comments, please watch that section where I'll discuss the known quirks with this particular implementation. Let's get into the high-level architecture. Okay, I've got the final implementation of the program right here, and we're going to discuss the architecture a little bit. So this is a thread pool and Epoll based server. What do I mean by that? Epoll is a mechanism by which a single thread can wait on multiple file descriptors at once and choose to handle whichever one is ready for I/O at a certain period of time. So for example, if I've got one thread and I'm watching 5 file descriptors and file descriptor number 3 is ready before any of the other ones, I can just go ahead and handle that, and I don't have to wait for all of the other ones to have an event before I can continue. This essentially saves me from having to spin up a new thread to watch every file descriptor, and we can just block until any of them are ready. And now a thread pool is where a program will grab a whole bunch of threads at some point during its execution that it can delegate work to. The threads that the program grabs can also be referred to as workers, and we're going to refer to them as workers in this video. So essentially, this is the architecture of our program in a nutshell. I am getting a whole bunch of clients, like I grab a thread pool of a certain number of threads, and then every client I receive, I can delegate to those threads, and each thread can wait on a certain number of clients. So each thread is capable of handling a certain amount of clients. I have these defined here. So as you can see here, I've got a constant defined max workers is 8. So that is how many threads my program is allowed to spin up as workers. And here I've got a max table size, which is essentially the maximum number of clients that I can have. And I'll get to the table in just a minute. And then max clients, this is actually per worker. So this is just max table size divided by max workers, which is pretty self-explanatory. So in this situation with the constants I've got defined here, we can have 32 clients per thread. That's essentially how many I'm going for here. Now, other high-level architecture stuff, I want to turn your attention to this function right here. This is my worker thread. So every thread that I spin up is going to be an instance of this function here. Now, basically what this one does, as you can see here, I'm waiting on an Epoll event. And then you can go ahead and loop through every Epoll event that you get. So every file descriptor that has an event, you can just loop through those and handle them dynamically without necessarily knowing which one is which. So that's essentially what our thread does. And here you can see down here, I've got a network loop for the protocol that we're implementing. Now the protocol that we are implementing with this particular server, I've done a video on. It's this one right here. The video I did is not a prerequisite. This is a very simple protocol, which has all of its stuff defined here. So it has an action, which basically says, I want you to do this. It has an option for each action. So that means I want you to do it in this way. And it has a payload, which is an array of strings. So it's a very simple protocol. If you want to see me actually write up the implementation, this is just it's got serialization and deserialization. I'll link the video where I do that in the description. So that's our protocol. The clients that our server is actually going to be serving are called RolexHound and Smartwatch. And I made RolexHound in my very popular video, How to Write a Linux Daemon. It's essentially a file event watcher. So what that means is that you can tell it to watch a file, and if that file is changed in any way, it'll send you a desktop notification. In the same video where I wrote up this protocol, by the way, I split that single program into two different programs, one of which is the file event watcher and the other is the desktop notification program. The desktop notification one is called smartwatch. Okay, all of that explanation out of the way, you can see how this is lining up. So this server's job is to let RolexHound and smartwatch communicate with each other. So smartwatch will say to RolexHound, hey, I want you to watch this file, and the server, it'll send that to the server, and the server will forward that on, and RolexHound will start watching that file. Similarly, RolexHound will say, I have a file event, I want you to send a desktop notification, so it'll send that to the server, and then the server sends that to the desktop notification program. Now, this is where I actually gather my thread pool. Right at the start, you can have a thread pool that grows or shrinks as your program progresses, but for the sake of brevity, we're going to do a static thread pool. So right here in my main function, that's where I'm at. As you can see, we loop through our max workers, and down here I've got a pthread create, so we are spawning the max workers amount of threads right at the beginning of our program. I want to turn your attention to these data structures up here. So we've got a private worker data struct, which is exactly what it sounds like. This is data that only the worker has access to. And then we've got a shared worker data struct, which is shared between all workers. And this is actually a member of the private data struct. Now, if you think about the model that we're going for here, I don't know if you've ever heard of publisher-subscriber before, but our server is going to handle publisher-subscriber model. Essentially, it makes sense that if you've got RolexHound who's saying, hey, I've got file events, and smartwatch, which is saying, I want to listen for file events, RolexHound is a publisher, and smartwatch is a subscriber. So smartwatch tells the server, hey, I want to watch this file. The server will have to add it to some sort of cache that says, okay, you want to watch this file. And then when RolexHound sends an event for that file, it says, okay, well, I know this person, and this person want to listen to that file. So we're going to need some sort of data structure to link our subscribers with what they want to subscribe to. Subscribe to me, by the way. So essentially, if you think about how we could do that, the data structures we could use, the most obvious one is a hash map. So essentially, you have a hash map where the key is the path of the file that you want to watch, and then you might have an array of clients or something like that that are subscribed to it. And if you were doing this in a higher level language where that's built in, I would say absolutely go for that. Because I'm introducing a whole lot of new concepts here as well. I'm not actually going to implement a hash map in this one, or a linked list, which is the second data structure you could use for this. We're actually just going to use an array. So that's what I mean when I said table before. So as you can see right here, we have a table, which is essentially just an array of these watch entry structs. So this is an entry in our table. We've got a subscriber file descriptor, which is the file descriptor of the subscriber. We've got the path that that subscriber is interested in watching. This publisher file descriptor links the path to the RolexHound instance that is publishing that. And we have this active files here, which is part of a very primitive load balancer that we're going to be implementing, which is basically, so if you have a look up here, you'll see I've got a max files defined as 8. So essentially what that means is that each RolexHound instance connected to our server can only handle 8 files at a time. That's not a limit on RolexHound, that's what I'm saying here. So every time a RolexHound instance has 8 active files, I'll try and allocate that to a different one to sort of balance the load. Now this table right here is defined with this max table size. Now what you could do is statically allocate that right at the beginning of the program and say, I'm going to allocate all of this memory, but I'm going to use this to introduce another subject, which is chunk-based allocation for memory. Now, as you can see here, I've got a table chunk and a max table size. So essentially what this means is that we're going to start off with a subscriber table that is 8 indices long. So that means when the program starts up, I can only handle 8 clients. If a 9th client joins, what I'll actually do is reallocate more memory to that table in a chunk, right? So I'll allocate 8 more indices for, clients to join in until I hit this max table size, at which case I will not accept any more connections. So that's kind of the high level architecture of what we're going for here. It's a publisher-subscriber model with Epoll in our threads to handle multiple events, and we're doing a thread pool where we can sort of delegate load to each thread. Okay, it's time to talk about everybody's favorite thing, which is the known quirks with this implementation. Now, the first one here is this max table size is assumed to be the max client size. Now, technically, one client can subscribe to multiple things, in which case it'll actually take up more spots in our table. So it's not always technically the max number of clients, even though that's how I've defined it here, where I assume, one client is only subscribed to one thing. Essentially, if one client subscribes to two things, that just means that one less client is able to join because it'll never be able to allocate a subscription in the table. As you can see here, I will not be checking the return value of my memory allocations. I know, but listen, we're writing 600 lines of code in one video, okay? Every time I allocate memory, I am not going to check it. Otherwise, this video would be 3 hours long. It is trivial to go in and add checks for this after the fact to make your implementation more robust. But for the sake of this video and it not being 3 hours long, every time I allocate memory, I will not be checking. I mean, besides, my computer has 64 gigabytes of RAM. How about yours? Right after we read from our network socket, we jump straight into a deserialize, and this deserialize function ignores everything after the first packet. So technically, if a client sends two messages really, really quickly, we will drop the second one and only read the first one. So that's essentially if this read call returns more than one packet in that data, we are not going to be able to handle that. The way you could solve this is by having the deserialize function maybe return the index of the next packet if it finds that there's more data after the packet it just read. And then you could implement a sort of wraparound buffer where you then store the results of that in the new buffer and then read the rest of the packet into the next one if it's been fragmented. And you can do that until the end of time. Now, the last quirk I want to talk about is with our primitive load balancer. Now, here, when I actually go and allocate clients, this is where I go ahead and do it. And you'll notice that essentially what it does is it fills up our threads one by one, which is not technically what you might want. You might want them to fill up evenly. Now, the reason I've done it like this is because I could go ahead and do it the other way, but it would introduce a couple more loops. And this is already a 600 line program. But basically the way you might do it is every time you allocate a client to a thread, you increment the thread ID. And then as long as that thread has space available, you can add the next client to that, increment the thread ID again, and sort of go along. But then if a client leaves, then you can't necessarily do that because thread 2 might have space available, whereas your index is up to like thread 5. And thread 5 might be completely blocked. And then you increment that to go back over to thread 1, and you've got a whole massive problem. So if you find that the thread that you're currently on doesn't have room, you can just go ahead and do this where you search the entire thread table to find one that's available. Okay, enough talk, let's get coding. I've given myself to start off here the hash includes that we're going to need and the hash defines that I explained earlier. These extra ones here are just error conditions, which will be pretty self-explanatory. And these ones down here are bit masks because our table search function is going to use bit masks to identify matches. And you'll see what I mean when we get to it. Other than that, I've just got the Epoll library and the socket library because those are the ones that we're going to be needing. And I also have pthread.h up here because that's what we're going to use to spawn in our threads. So let's get started by defining our program title, which is going to be Flex HQ. Because we've got a Rolex, we've got a smartwatch. This is the server that connects them. This is the Flex headquarters. All right. Now the next thing I'm going to create is a mutex, which is a print lock. Now a mutex, if you're not familiar, is just a lock such that if a thread wants to access a shared resource, it can lock it so that no other threads can access it while it's being accessed. This avoids what we call race conditions, where two threads try and use the same resource at once. And essentially, if you notice like that when your threads are printing stuff to stand it out, it kind of gets mangled. It's because they're both trying to print stuff to stand it out at the same time. So I've just got this print lock here to lock that in place. Now we're going to need a couple of data structures here. The first is our watch entry, and I explained what everything in this does in our architecture section, so I won't be explaining it here. Go back and watch the architecture section. It should be pretty self-explanatory though. So we just define these and finish it off with a semicolon. I always forget the semicolon at the end of my structs. So now we're going to make a struct for the shared worker data, which is going to contain our subscriptions table, which is just an array of these watch entries right here, which is also pretty self-explanatory, I hope. Now, we're going to need to keep track of the table size. So we're going to have a sub table size. And the last thing we're going to need is a lock. It should be pretty, I hope it's pretty clear why we need a lock on the subtable, because this is explicitly mentioned as a shared resource. We need to lock it every time a thread wants to do work on it. Now we're going to give our private worker data. And now keep in mind that because this data here is private, we don't need mutices for anything. Is it mutices? I'm going to say mutices. We don't need mutices for anything in this struct. And the reason for that is that the reason I've made this distinction here explicitly is such that we know always what each thread only has access to and what's shared. So we're going to define a couple things. The first is the thread number. So when our thread pool gets allocated, we're going to give them all numbers, and they need a pthread thread ID, which is used when we spawn them in. We're also going to need the shared worker data pointer. So we're going to have one shared data struct, which is pointed to in every one of these, and we're going to have one of these per thread. I hope that's pretty clear. We need a file descriptor for our Epoll events. We need a file counter table, which basically, if you remember from the architecture section, I said that, each Rolex hound can only watch 8 files. This is going to keep track of how many files each Rolex hound does. And we say max clients here because theoretically up to every client a thread is allocated could be a Rolex hound. So to keep track of that, we need an index for each. Now we're going to define 2 Epoll event structs, and I'll explain why we need these. So the first one I'm going to call socket events, and this is also going to be max clients. And the second one I'm going to call socket event queue, and I'm going to say max Epoll events. Max Epoll events is basically how many Epoll events we can handle at one time. This can overflow, by the way. The Epoll documentation says as much. So if you handle too many too quickly, you might drop them. But 8, I just like 8 as a number. So this one here, basically, is going to hold the file descriptors for all of our connected clients to our server. And this event queue right here is going to hold all of the events that our thread is waiting to sort of register. And we need to register the socket event with the file descriptor of our client in Epoll. And you'll see when we do that why that's necessary. And the last thing I'm going to need is a socket events lock. Because the only resource in this private worker thread that's shared is this socket events and the event queue, because our main thread needs to access that to allocate our clients. That's the only shared resource in this private worker thread, so I'm going to make a mutex for it. I just realized I called this private worker thread. It should be private worker data. Now we're going to make some helper functions for these structs. They're just initialization functions, basically. It should be pretty self-explanatory why we want these. Essentially, we just want, every time we initialize a struct, we want it to be initialized to some sort of set of known values such that we know every time we have an uninitialized struct that we're dealing with. So we're just going to go ahead and set them up for all of these. So subfd is going to be 0 in our watch entries. We're going to have, it should be called entry, not event. Got Epoll on the mind. Watch path should be null. Our publisher file descriptor is going to be 0. And our active files is also going to be null. So we're just setting our pointers to null and our file descriptors to 0. We're going to make another function called watch entry reset. And the reason we're going to do this is essentially it's a teardown function. So entry watch path is not equal to null. We're going to free it. And then we're just going to call watch entry factory on the entry to reset it. So this basically, like, if we've allocated memory for this watch path, we free it and then we reset it. So this should be called every time we've got an initialized struct that we want to reset to defaults, because it'll clear out our memory and then reset everything. So we're going to do the same thing for our private worker data, where we're going to say thread data, thread num is equal to -1, thread data epoll fd is -1, thread data shared data is null, and here we're going to go ahead and initialize our socket events. Now this is a member of the Epoll events, so .data.fd is where you set the file descriptor associated with that Epoll watch item. So we want to set it to 0 so we know that this client ID basically is free to be allocated to Epoll as a watch thing when we receive a new connection. That's why we're doing that. And similarly, we're going to set the file counter table index to -1. So basically that means this client is not Rolex Hound currently, and it could be in the future. So that's it for that one. Now we're going to do an initialize data table function. So this one right here, give it a start, give it an end, and give it our table. Basically all this function does is it loops from our start value to our end value and initializes with our function up here all of the structs that are present in that section of the table. We're going to need to use this when we reallocate a new chunk to our table, basically. The last helper function we need to create is kind of a lengthy one, and it's going to be our table search function. So if you think about what this function is going to be doing, every time we need to find an element in the table, we need a way to actually go ahead and do that. So we're going to make this find table entry. We're going to give it a watch entry as the match ID. So essentially, our caller is going to set its parameters that it wants to be matched in here, and this function is going to try and find those parameters in the table. So now we're going to need the table size, we're going to need the actual table itself, and we're going to need a uint32 that we're going to be calling match mask. And finally, I'm going to put in a boolean for clear. So basically the match mask specifies what values in this actual struct we want matched. So for example, if we are only interested in finding the subscription ID, that's when we use this bit mask up here, and our function knows, okay, we only care about the subscription ID part of this watch entry. We can use this bitmask method to search for multiple things at once. So for example, subscription ID and publisher ID, you just OR these two together and it'll find it based on what's in the match entry struct. And clear at the end is basically just like if we are wanting to clear the match, like get rid of it from the table and reset it, then we put boolean clear in true when we call the function. So this is going to need a match uint32 here for actually like setting our boolean flags for each of these. So now we're going to need a match counter just for, you know, statistics sake. We can print that out to the user that we found. In the case of clear, we're not going to return a single int, like a single index. We're going to go ahead and clear everything that matches. So this match counter variable here is going to count how many entries we clear from the table. So now we're just going to loop through the entire table. And we are going to set matched equals to 0x1, 2, 3, 4, 5, 6, uint32. Technically you don't need to do that, but I like to do it just for, you know, completion's sake. And now we're going to check every entry. So for example, we would go if match entry.subfd equals table I.subfd. So we're checking the value of this, then matched or equals with match subfd. So we found a match for our subfd. Now we're going to go if match entry.watchPath equals null, if table I.watchPath also equals to null. You guessed it, guys. We have a match. So we're going to OR that equals with match path. If this is not equal to null, then we can check the value of these. So we're going to say if table watch path is not equal to null, and not strcmp. So this is like, if the value of strcmp is 0, which means it's matched. Match entry.watch path and table I.watch path. Then we have a match for the value of our match path. So we can say matched or equals to watch path. I explained bit masks in my how to write a Linux daemon video, by the way, if you haven't checked that one out already. So now we're going to check the publisher ID. So if match entry.pubfd equals table I.pubfd, you kind of get the idea by now. Then matched or equals to match pubfd. I'm actually going to introduce another variable up here, and it's a surprise tool that'll help us later. So this is going to be an integer, and it's going to be called any pub magic val. It's a magic val, and you'll see why in just a minute. So now I'm going to OR this with match entry.pubfd equals any pub magic val. So if you think about what this is going to do, if our publisher FD in our match entry is set to any pub magic val, we're just looking for something with a publisher ID, essentially. And I'll show you why that's useful later. So if table I dot active files equals null, matched, or equals with match available. So essentially what this means is we've got a table entry where this is set to null. So i.e. there is nobody who is subscribed with this struct at the moment. It's a free struct that can be allocated for a subscription, basically. Because every time we allocate a subscription, this pointer will not be null. You'll see that when we actually go ahead and implement that particular function. So we can say match available there. Otherwise, so if this is not equal to null, then we can compare if the dereferenced value of that, and now we can dereference because it's not null, is less than max files, matched, or equals with match unloaded. So if you think about this here, we're saying this Rolex Hound instance has active files less than max files, so he's unloaded. That means we can use it to allocate more files to it to watch. Now the last thing we're going to do is check our mask. So if matched and match mask, we're just doing a bitwise and, equals match mask. So if matched ANDed with the match mask that we specified we want to look for is equal to the match mask, then we can say match counter plus plus, because naturally we found a match, unlike my Tinder profile. And if clear, what we're going to go ahead and do is reset that particular entry. So watch entry reset on the value of the table. And we're going to continue, because the next line we're going to say is watch entry factory on match entry. So we're going to reset the match entry. And then we're going to return I. So if you think about the purpose of this function, if clear is false, the purpose is to find an index in the table that matches our description. So naturally, if we find a match, we want to return I here, which is our index. But if clear is true, then we want to clear everything in the table that matches that description. So naturally, we'll reset it, and then we'll just continue the loop. So we'll never hit this return value here. Now, the last thing that we want to go ahead and do with this function to finish it all off is say watch entry factory match entry, because in this case, we are exiting out of a index search. So we need to reset the match entry struct so we can use it again later. And we are going to return match counter, which if you recall, is the number of matches that we found in the table that if clear is true, and if clear is true, that's the only way we get here, that we've cleared from the table, just for statistics' sake. Okay, you made it past the boring part. Let's have some fun. Let's write the main function. I'm going to go ahead and give myself all of these here to save you from watching me type them out, but essentially we're just setting up some variables we're going to need. So we've got a client ID, a thread ID, a socket file descriptor for our server, a client file descriptor variable for our incoming connection, and I've just got some of this additional stuff here for the socket servers. I'm not going to really explain what each call does in this video because I already explained that in my implementing a network protocol video. So if you want to know the basics of a socket server, go and check that out where I do end up covering that. And here I allocate our, shared data, which is there's only one of, and I've got our thread worker table, which is an array of these private worker data. So this is essentially an array that stores all of the data associated with our thread pool. I've also allocated this subtable here with size for our first chunk, and then set the size there, and then I initialize the data table with that function we created earlier. Okay, now we're going to do something interesting. We're going to initialize our mutices. Again, I don't know if that's the correct way to say it, but if you remember before, I had some mutices that I initialized. Well, I defined. We actually have to initialize them. So we're going to go ahead and do that here. This is the call that you use to do that. It's pthread mutex init. You give it the memory address of the mutex you want to initialize, and this is just some flags. I don't really care in this instance, so I'm going to set that to null. And I need to initialize two, so I need the standard out one, and I also need the, of course, the shared data table one. So the subtable lock for our subscribers equal to null there for the flags. And now I'm essentially just going to go ahead and implement some error conditions. I'm not going to bother typing those out because this video is going to be super long, but here I'm just printing a standard error, couldn't create mutices with the title of the program, and I exit with this condition. Now, we're going to set up our socket. So if socket fd is equal to socket, so we're creating a socket here, we're going to use an internet socket, and we're going to use a sock stream with the protocol 0. So we're creating this basically means we're creating a TCP socket. We're going to use TCP. You could also use Unix sockets for this, and it would be the same effect, but replicating it with UDP, it might be slightly different. So -1. Again, if you want to see me cover exactly this, like what all of these things mean, check out my implementing a network protocol video where I actually explain what these do. So I also need to include a whole bunch of this stuff as well. So I'm just setting the server address to be zeroing it out. I set the family of the server address to inet. The address, I don't care because we're the server. And then the port, I need to do htons on the port that we defined up here. So basically we're just saying we've got a server on any local address with this particular port, and it's an internet socket. Now what we can do is bind to that socket. So essentially we're just saying, hey, I want this socket, on this address, can you give it to me? So that is sock_adder of that, and the server address struct that we just defined, size of server address equals -1. This is our error condition. So we're just going to print an error and exit with socket bind. Pretty chill, pretty chill. Now I'm going to go ahead and just print a status thing. So printf, our program title is about to spawn worker threads supporting worker clients, like this number of clients each. So like just a statistics thing, because you could change those parameters if you wanted to. Now we're going to loop, and this is the part where we actually create our thread pool, which is really, really cool. So for int I equals 0, I less than max workers, I plus. So we're going to create our threads here. So the first thing we want to do is call our private worker data factory on our worker table elements. And the reason we do this is because we haven't done that yet and we want to initialize them. So pretty simple. Now we're going to create an Epoll instance for each worker thread. So thread worker table i.epollfd is equal to epoll create 1 with the flags 0. Now, essentially what this is doing, and you can check the Epoll manual page for this, but my, LSP is going to be very helpful here. But we're creating an Epoll instance. So we're saying, hey, I want to use this FD to check multiple file descriptor events. And the flags parameter can be 0 for this instance, because it used to be size, but that was deprecated. So now you can just put 0 and it's chill, it's chill. But now we're going to have to check the value of that. So if thread worker table i.epollfd is -1, which is the error state of creating Epoll, we're going to exit with another exit condition here on Epoll. Pretty chill, pretty chill. Now we just go ahead and set the shared data to the address of our local shared data variable here, because of course there's only one of them and we want it to apply to everybody. And the thread number is going to be this current loop value here, I. Pretty simple, you know. Now, if pthread mutex init, because remember, we need to create the socket events lock. If you go back and look at our struct up here, each private worker data instance is going to have this socket lock. So we need to initialize these mutacies as well. So we're going to go ahead and do the address of thread worker table I dot socket events lock down here, null as well, and then it does not equal to 0. And we can just go ahead and exit with yet another error condition. Just error initializing thread socket event mutex and exit out there. Now, this is really, really cool. We're going to create our thread, which is what I'm most excited for. So if pthread create, now the thing to note here is that we are going to use the thread worker table ID. We need to give it a pthread t like ID. So we're going to use thread ID, which is a pthread t. That's the first argument. I'm going to give this parameter null because we don't necessarily care about that. This next parameter here, though, is going to be our worker function. So we're going to have to go ahead and define that. So I'm just going to put that as null for the moment, and we'll finish writing this thing so my LSP will stop complaining, and then we'll go and create that worker thread function, which is going to be really cool. And now we're going to do the argument that we want to pass to it. So it's a void pointer, basically. So if you think about that, we want it to be our thread worker table I, because that's our private worker data that this guy is going to have, and it's a pointer, so we need to give it the memory address here. Does not equal to 0. And again, we can exit with another error condition. Now to round off this thread pool initialization function, I'm going to just go ahead and put in these status values here. So we lock the standard out lock, we print spawned thread with the ID, and then we unlock. So that's creating our thread pool. Now we've actually got to create a worker thread function for our thing to actually use, which is really, really cool. Okay, this next part might get a little hectic, but bear with me. We are going to create a void pointer return function. So this is going to be called HQ worker thread. And it's going to take another void pointer. Lots of void pointers today. I'm going to call it void thread data. So every function that we pass to pthread create needs to be of void pointer return type, and it needs a void pointer as an argument. So in this case, we'll be passing our private thread data struct in as a void pointer. And now we are going to have to go ahead and cast it. So struct private worker data, and I'm going to call this one worker data, is going to be struct private worker data cast of void thread data. Pretty self-explanatory, right? We receive this pointer in here, but we always know that it's going to be a private worker data, so we can just go ahead and cast it. I have all this other init stuff as well that I'm not going to bother typing out. We've got socket buffer here. This is just our socket server receive buffer. We've got our client ID for various things, and all of these you'll see when we get here. So bytes we read from the socket, events ready, how many events our Epoll FD is giving to us. Watch index and subindex and client ID are going to be used in our network loop that I'll go over later. Again, for our network stuff, we need flex message, read message, and send message. This is just part of our network protocol that we made in a previous video. The result of serialization, again, previous video. The watch entry, so match entry. If you remember our crazy function up here, this is where we're actually going to use it, right? Because we got to find entries in the table. And then our shared worker data, shared data. I've just done short form here, so we don't have to keep referencing it by this value. This full value here. Okay guys, so the next thing that I'm going to go ahead and do is call our factory functions on all of these structs. So that we make sure that they're initialized after we define them to our predefined values. Now it's time to do the loop of this particular thread. So we're just going to do a cheeky while true. Every daemon or thread worker it's a while true loop, guys. That's all it is. What makes a daemon different from a regular program is a while true loop. So now we can actually wait on our Epoll instance to give us something. So Epoll wait is the function call that we want to use, and it returns an integer with the amount of Epoll events that we need to be able to handle. So we can use events ready is equal to Epoll wait, and the first argument here, as you can see, is the Epoll FD. The second argument here is the events, essentially array that we are wanting to store the metadata associated with the event in. The max events that we want to read, and you can add a timeout parameter if you want to, but I'm not going to because we want to block on all of these events per thread, so we don't need a timeout value. So our Epoll FD is, of course, our worker data Epoll FD. That's in our private worker data. Where we're storing the events is worker data socket event queue, and max Epoll events is of course our max, and -1 for timeout because we don't want one. So if events ready equals -1, this is an Epoll error condition. So basically we're just going to do the same thing as we always do, which is exit with an error. However, because we're in a thread now, we need to call pthread exit. And you can give it a return value, but I'm not going to check these ones anyway in this program, so I'm not going to bother. And we print out what the error is to our log, so I don't really care to give this a return value. But pthread exit is what we use to exit out of a thread and not the entire program. Like in main, we use exit, and that'll kill the entire thing, but we're just going to exit this particular thread. Now we are just going to print some metadata. So basically, print we got this many events, and events ready there shows how many events we've got. Now we can loop through all of our events. So we're just going to go ahead and do for int I equals 0, I less than events ready, I plus plus. And what I'm going to do now is call flex message reset on send message and read message. And the reason I'm going to do that is because this is our network loop, guys, right? So we might be sending and receiving certain things in our network loop, and I'm just going to reset them at the start of the network loop so we know that we're dealing with fresh structs. So I'm also going to set sub index is equal to -1, watch index is equal to -1 because we use those later. If you remember, the whole point of this function is to find entries in our table. So I just want to make sure that every index we found in the table later on is initialized back to 0 at the start, back to -1 when we, restart our loop. So now what we can do is lock the socket events. And the reason we're going to do that is because I want to find the client ID of the client that is sending, of the person who sent us a message. So I can lock the mutex for worker data socket events lock. And now I can loop through and try and find that. So we're going to do for int j. Now remember, we have to use a different value than I because we're already using I. So j is equal to 0, j less than max clients. Don't know why my IDE keeps doing that, but j plus plus. Now we're going to check if worker data socket events j.data.fd. And remember, this is where our file descriptors are stored for our that Epoll is going to be using. Worker data socket events q i.data.fd. So think about what we're doing here. We're looping through our entire clients that we have available, and we're checking if that client's file descriptor is equal to the one that we just got in this Epoll event. In that case, client ID is equal to j, and we can break. Now down here, we can check if if client ID was equal to -1, and we can just say we couldn't map the client ID and continue because we don't want to have a situation like that. Technically, that shouldn't happen, but maybe it could. We just want to be safe. Now we're going to actually read from our socket. So bytes read is equal to read worker data socket event q i.data.fd. Again, this is the event that we just got. And we're going to read it into socket buffer, and we're going to do size of socket buffer. And here we can just check if bytes read is equal to 0 or bytes read equal to -1. That's an error. So our client has probably terminated the connection. So what we're going to do is we're just going to print out our error condition as per usual. And we're going to do this. So sub index is equal to worker data socket event q i.data.fd. what I'm going to do is essentially clean up this client's information. So before I do that, I want to store a reference to the file descriptor value so that I can do more operations with it later after I've even closed it and reset it. So, and by that I mean like cleanup, not actual like writing, because of course that wouldn't work. So Epoll CTL is the one to use for adding and removing things from Epoll. Now, the first argument here is the file descriptor for our Epoll instance. So worker data, Epoll FD, of course. The second one is the operation. So I'm going to use Epoll CTL del for delete. So we're deleting an Epoll event. And now I'm going to do worker data, socket events, and here's where I use client ID. Because I know that we're getting rid of this associated Epoll event struct from the thing because we found the client ID in the loop up above. And the next argument I want to be giving it is the address of the Epoll event. And this should actually be .data.fd, I believe. Yeah. .data.fd, because this is actually the file descriptor associated with the Epoll thing that we're trying to get rid of. Now then, we can close that. And this is why I wanted to take a reference of it beforehand, because we're going to close it. We're going to set it equal to 0 in the event queue, actually. And I'm going to set that as I. And then I'm going to zero out the socket event struct. So in our socket events thing, I'm going to zero that out. So we clear it. So we tell the main thread, hey, look, you can, do something else with this now. And then I'm going to unlock our socket events thing, which I should have locked up here, as you can see. So here I unlock it in two places. On this continue condition, because I don't want to deadlock, and down here, because, we don't need to do anything with it anymore. So if we read something bad here, like if we've got an error, I don't want to continue trying to evaluate the network loop. So I'm going to continue, and then I'm going to grab this mutex unlock and put it down here, just in case. So if we don't get an error, we're still unlocking. Now that we've sort of created a sort of skeleton for this worker thread, we're actually going to go back down to main, and we're going to set up our socket listener, which is another really cool thing that we can do. So if you remember where we were up to in our main function, we just allocated our thread pool. So now I'm going to listen on my socket. So if listen sock fd 1, so if this value is non-zero, that means it errored out. So we're just going to go ahead and exit on socket listen. If not, we can just go ahead and print a cheeky little metadata thing here that our program is listening on this port just for logging purposes. And now we can actually set up the accept loop of our main function. So this while true loop right here is just going to listen for connections and accept them. So if client fd, remember that's our client file descriptor, equals accept on our socket fd, we've got to give it the sock adder casted pointer of client address and sockland pointer of address size, and then -1 is the error condition for this. Then we're going to exit because we failed to accept this connection here, and that's an issue with our socket most likely. Again, I can just go ahead and print out some metadata here for accepted a connection. You might have noticed I'm not always locking standard out because, and I do apologize for kind of speedrunning this video a little bit, but it's going to be pretty long, so I don't want to faff about. So now I'm going to set thread ID equals to -1 and client ID equals to -1 because this is the section of the program where we're actually going to decide which thread to allocate the client to. So we're going to do a little loop here. So I equals 0, I less than max workers, because we've only got that number of workers available to try. And I'm going to go ahead and lock the worker table socket events lock, because I want access to this while I'm trying to allocate, and I don't want them changing it while I do so. So now for int j equals 0, j less than max clients, so we're looping through the entire queue of, the entire socket events structure of that worker to see if we can find a free spot. So if thread worker table I dot socket events j dot data.fd is equal to 0. Now remember, this is what we said was our uninitialized value. Then we can say client ID is equal to j and thread ID is equal to I, and we can break. So we found our client ID and our, thread ID. So if client ID is does not equal to -1, then we're going to break out of this loop. This should actually be, yeah, sorry, my bad. So if we found something, we're going to break. We're not going to consider any more workers. And now down here, we are going to, actually, I need to unlock that mutex. So we're going to unlock this guy down here. And the reason that we're doing it down here instead of before the break is because if we found a client ID and a thread ID, then I'm going to keep using this event. So I don't want to unlock the mutex yet. So if thread ID is -1, so that means we couldn't find something. Here's what we're going to do. We're going to print to stand it out that we couldn't, that, too many clients were active, and we're going to terminate the connection. We're going to close the connection, and note that I don't have to unlock the mutex here because that would already be done for me because this loop will complete. It won't break early. So if we get here, we can assume that we have a valid place to store these clients. So what I'm going to do is thread worker table thread ID dot socket events client ID. So we're actually allocating dot events is equal to epoll in. Now, if you remember, this socket event is an epoll event struct. So when we say dot events, we are determining the kind of events that epoll will look for. There are two main ones that we want to consider. So epoll in is associated with read events and epoll out is associated with write events. Now I only care about reading for these ones. So I'm going to say epoll in for this particular one. In fact, we don't actually care about available for writing in this entire program. So epoll in is the only one relevant to us. And now we're just going to set the file descriptor for this. So .data.fd is equal to client fd. So we've set up our epoll event struct to queue ourselves up for events, basically. Now we've got to actually tell epoll to add that. So what I'm going to do is if epoll ctl, if you remember earlier, this is the function we used to add and delete stuff from epoll, thread worker table thread id dot epoll fd. So that's the epoll one we want to add for that particular thread. And this time our operation is epoll ctl add. We did del last time. We want to do the client file descriptor and the event, like the struct that holds our event settings is thread worker table thread id dot socket events client id. And the error code of this is anything non-zero. So if that's non-zero, we can go ahead and do this. So we couldn't add the socket to event poll. We unlock the mutex for this particular client. We close the file descriptor and we continue. So that's what we're going to go ahead and do there. Now, if we're here, what we can do as well is unlock this mutex. So mutex unlock thread worker table thread ID, because we are done with this, by the way, like whether or not we continue or not. So we're going to unlock that. And the last thing we're going to go ahead and do is print more logs. So if you think about what this function has actually done, we've accepted a client, we've found a thread for it to be allocated to, and then we've added that client's file descriptor to the epoll instance associated with that thread. So now when we go back up to our thread and we are waiting on epoll, by the way, epoll wait is dynamic, so you can add and remove stuff while it's waiting, which is really sick. It will be able to handle that. So that's awesome. That's the crux of the entire thing. The last thing we're going to do in main down here before we get back to writing our handler is we're going to change this one here from null to our HQ worker thread. So essentially, because we've just created it. Now I actually have to think very carefully about how I want to do this next section. So we're coming back up to our worker thread. And the next part of this is going to be handling the events of our custom protocol. And I feel like that is slightly outside of the scope of this video because I'm trying to teach you about the paradigms of Epoll and thread pools. So I'm just going to kind of run through the basics of what we're doing, but I'm not going to explain it as in depth as I have the other things. So we're going to deserialize our message and get our custom protocol stuff. We're going to do a switch statement on the action. So we're going to decide, like, see what the client wants us to do. And we got a couple of cases here. So the first one that we're going to cover is the status. Now, if you remember from the architecture section, I said that he can register, Rolluxhound can register himself. And so what we have to do now, if you think about it, is we actually have to allocate that on the table as, hey, this is a Rolluxhound instance. So what we're going to do is lock the subscriber table. What Rolluxhound is going to do when he initializes himself is put himself onto the subscriber table and just have himself initialized there as a publisher. So he's going to take up one entry in our subscriber table. So we're going to use that funky little function that we called earlier. And this actually is in scope of the video. So match entry watch path equals null, pubfd equals 0, and we're going to use this find table entry with these parameters. And the reason we're doing that, we want to find one where the watch path is null, so it's an empty, like no one's watching, and the publisher FD is 0, so no Rolluxhound instance is owning that. And if that meets the conditions, then we can initialize Rolluxhound on that table entry. So we're going to do something here where we just say, if watch index is equal to -1. So if we couldn't find like a watch instance for him to go to, then, there's no space in the table for our new Rolluxhound instance. So that's sad. But if that is the case, then we can set the file counter table to 0. So now we've said, okay, this client is a Rolluxhound instance. He's watching files and he's not watching anything at the moment. Because if you remember, this value used to be -1. Now I'm going to do all of this stuff right here. So I'll explain what it does. Basically, we are saying that the shared data subscriber table at this watch index, so the one that we just found, the active files is equal to the address of the file counter table, so this one we just set here. So active files is equal to this memory address, so 0, and the publisher file descriptor is equal to the socket event that we got from Epoll, so this data FD. We're going to unlock the mutex because we're done with it, and Rolluxhound instance has been initialized here. Now I'm actually going to go ahead and continue instead of break. So the next thing we're going to go ahead and do here is if we get a watch event. Now a watch event is the case if somebody wants us to add or remove something from the watch table. So if you think about this, this is actually a subscribe or unsubscribe event. So we're going to do the same thing. We're looking for a subscriber ID where that equals the current client who sent us something. And the watch path is going to be equal to, so read message data 0 is the path of the thing they want added or removed. So what we're trying to find here is where this guy who sent us the watch add or remove request, if he's watching something with the path already, then we are going to find out. So this next thing that we're going to go ahead and do, so if the option is remove, now again, this is part of the custom protocol. If the option is remove, we're going to check. So if the sub index is less than 0, he's not actually watching it. So we didn't find an entry in this table. We can't remove the request. So we're going to unlock the mutex and go back to the beginning of our loop. Otherwise, we can just reset the table entry with that helper function, unlock the mutex, and continue our loop. Otherwise, what I'm actually going to do is break here. Because if this is not the case, if it's not a remove event, then it's an add event. And we're going to handle the add event, so for adding a subscriber, later on. So the next case we're going to do is a notify case. So this is the case if Rolluxhound is publishing an event. Now, publishing is within the scope of the video because we're doing a publisher subscriber model. So if this is a notification event, then essentially what we're going to do is loop through our subscriber table and find all of the people subscribed to that. So this is pretty simple. We lock the subscriber table, we're looping through. If the watch path is null, we don't care. Otherwise, we check if the watch path is equal to the path specified in the message that we just got from xoxo. If it is, we're using this watch index to count how many subscribers we send a message to. So we're going to zero that out, serialize the packet, and then write it. So that's pretty chill. That's pretty chill. The next thing that we're going to go ahead and do is all of this junk right here. So what this does, I unlock the mutex, again, pretty self-explanatory. And this is where I log, I published a notification to this many clients. And now here, so if watch index is 0, so we didn't find anybody to send this to, which is kind of sad, This is part of the custom protocol. We can send a remove request to xoxo himself with the file. So if you think about this, no smartwatch clients are subscribed. So we're going to tell xoxo, hey, you sent me a notification for this, but I don't actually have any subscriptions. Can you stop watching this file for the moment, please? And here I say as much, right? And then we just continue. And lastly, if we get a message type that we don't care about, we're just going to continue as well. So we're not going to bother handling the rest. Now, this next section is where we're actually going to handle our subscriptions. So in this case, like we've requested, can you add me to the subscriber table? So what we're going to go ahead and do real quick is try and find, a spot for this person in the subscriber table. So if sub index is greater than or equal to 0, and remember, we tried to find that earlier here. So we try and find, are you watching this file already? And if he's watching the file already, then we don't care. We're not going to re-add him. So he's already watching that file. But if not, because we continue there, so we can assume here that when he's not watching the file, we're going to try and find if a watcher for that file exists. So if xoxo is already watching that file, so we're going to try and find if another client is subscribed to that, and there's a valid path for that instance. And if there's a valid path, that also implies there's going to be a valid publisher associated with that entry. So we can use that in order to, allocate the new information for this client here. So if this is not the case, then we're going to do this. So if watch index is -1, and if you remember from our helper function up here, the match counter default value is -1. So if we loop through the whole table and don't find anything, that's what we'll return. So -1 implies that we haven't found anything. This is where we're going to use that magic val that I was talking about earlier. So if that's the case, if you remember, it's going to find any publisher FD. And that's what I want. I'm going to try and find if xoxo is actually on the server to service our request. So I can check for match pubfd and match unloaded. So we're looking for a xoxo with any publisher FD that is unloaded. That's what we're doing there. If we still can't find anything, then no xoxo is available, like on the server. So we're just going to continue. If not, what we're going to go ahead and do is write that request. Now remember, we're requesting to add something to the table. So if we don't have a watcher here, and if xoxo exists here, then all we're going to do is serialize, like forward that the packet we got essentially to the publisher FD, and that's why we're including that in our watch entry table. So that down here, now that we've found an entry in the table that's a valid xoxo, we can write to it and tell him that we want him to add it to his, watch queue. So then all we have to do is add 1 to the active files, which we can do by, dereferencing this pointer and then just adding 1. This is pretty self-explanatory stuff. Okay, so if we've gotten here, we know that there's someone who's able to service our request, and if not, like if it didn't already exist, we've asked it to. So this is the part where we need to actually add our smartwatch to the subscription table, so he knows, hey, I want to watch this file, and whenever we get a file event for that, we can just send it to it. So the first thing I'm going to do is search for an empty table entry to allocate this to. So to do that, we can use our match entry watch path and the active file, set those both to null, and find a table entry with the flag match available. So if we go back here, you can see what we're trying to find. We're looking for, active files is null so that it's not taken up by a Rolloxhound instance. And if watch path is null, then it's not taken up by a smartwatch instance. So we come back down here. The next thing we're going to go ahead and do is this check right here. So if subindex is equal to -1, that means there's no space in our table. So we couldn't find an empty entry. The next check I'm going to do is to check if, so we're looking to reallocate the table, like add another chunk of memory to the table. If that operation would exceed the max table size, because we don't want to continuously allocate memory forever, that's a memory leak by design, then we simply can't do it. So we're going to say, you wanted to exceed the maximum table size, we're not going to do that, so we just continue here. So if we actually can allocate this memory, like if it's less than our maximum table size, what I'm going to go ahead and do is set subindex is equal to shared data subtable size. So I'm going to save the current value of the size. And what I'm going to go ahead and do is say shared data subtable size is equal to subindex plus table chunk. So we're adding another chunk to this size right here. And now what I'm going to go ahead and do is shared data subtable is equal to cast watch entry pointer to realloc. And now with realloc, you have to give it the original pointer, so subtable. And now we have to give it the size. So we're going to do size of struct watch entry times our brand new size, which is shared data subtable size that we just allocated more space for, right? Now, it's an important note that realloc actually returns a brand new pointer. So we pass it in this one and it'll give us a new one. And this is why it's important to have it in a struct whose pointer doesn't change. Because if you think about it, way up the top here, if we put it in private worker data and we just have the table in here, every thread worker that we have gets that instance and like we assign the memory value, like the pointer at the start. When a thread tries to update that, it won't update the reference for everybody, which is why it's important that we put it in this shared data struct here, whose pointer doesn't change, because we can update it in there and then everybody knows that that is the go. So now the next thing I'm going to go ahead and do is this. So we're just going to print out, that we allocated another thing in the subtable. And then we can do all of this stuff here. So basically what this does is we are saying the entry in our subtable where we found an index for our new subscription, set the publisher file descriptor to the one that we found earlier. So if you remember earlier, we were looking for a Rolloxhound instance in the table. Well, we found one. So set the publisher ID to this. Set the active files also equal to the one of that particular Rolloxhound instance, and set the watch path as a duplicate of the read message that we just received because it'll tell it the path that we want to watch. Now this is important. So this is dynamically allocated. And the reason for that is that when we go ahead and clear all of our stuff, we do in fact free this memory. If you wanted to be clever, you could have all of the pointers to your strings basically just stored in like a global array, and you could avoid allocating double, but I'm not really going to do that because that's a bit more complex than what we're doing in this video. I just want to be able to free them as needed in a simple loop. So we're going to go ahead and do that, and we're going to set the subscriber FD, of course, to the one that we got from Epoll. And we need to clean up its instances in the subscriber table. So come back up over here to where our bytes read is equal to 0 or 1. And what we're going to go ahead and do is this. So grab this chunk of code right here. So this if statement right here, if you think about what this represents, we're asking, so we're back to this file counter table variable, which if you remember, is the number of files that a Rolloxhound instance is watching. So we're asking if the file counter table value for this particular client ID is -1 or not. Now, if it's -1, that means it's a smartwatch index. It's not a Rolloxhound index. So if it's not equal to -1, that means it's a Rolloxhound index. So what we're going to do is set it to -1. So we're uninitializing it basically. Set this match entry.pubfd to the subscriber index. So what we're looking to do here is remove every subscriber of this particular Rolloxhound instance. So you can see here, we set subindex is equal to the data FD that sent us something. So if we set pub FD here, then when we search our table down here with match pub FD, we'll find every instance where this, where the file descriptor for this rollout instance occurs in the table. And this time we give it the clear flag, so we remove it. Now I do add +1 here for our printout statement because a match counter starts at -1, so we just offset that by 1. And here down here you can see if it's a smartwatch index, then simply the subscriber FD becomes a subindex, and we do the exact same thing. And that'll remove, so if it's a Rolex Hound instance, not only do we remove the Rolex Hound instance, but we remove every subscriber status for that instance. Like, it's just all gone. And then if it's just the subscriber, we just remove all of their current subscriptions from the table. And we're done. All right, it's demo time, the part everybody has been waiting for. So I'll go ahead and make the project here. If I go build xoxo, we'll start it up. You can see we've got 8 threads that it allocated to our thread pool, each supporting 32 clients. So I'm going to start a Rolex Hound instance right here on my local host. You can see we initialize it at index 0 in the table. Now I have this script here. It's kind of cheeky. It's called testhq.c, and you can see we're just loading it up with a whole bunch of clients just to test it out. So if we do a word count on that, we've actually got, oops, my bad, wrong file. We've actually got 435 clients that we're going to spin up, and obviously that's bigger than the table size. So let's see what happens. So as you can see, we're going to start terminating, obviously, because there's too many. But we'll scroll back up, and you can see here, it is allocating them to the threads correctly. So you can see here, we've got table 94. That's as far as my scroll back goes. And it's being assigned to thread 2. And then as soon as we hit, so you'll notice we've got client 31 assigned to thread 2. As soon as we hit 32, which is our max, we'll assign client 0 to thread 3. So thread 2 is filled up. Now we're going to fill up thread 3. So many tongue twisters in that one. But yeah, as you can see here, we've also got more chunk allocations to our subscriber table. And if we just scroll down a bit, you'll notice that as soon as our table index hits 255, which is our max is 256 size, right? So 255 is the max index. We start terminating clients. Now then, theoretically, all of the remaining ones should be watching our file. So if I bring my editor over here, and I'm going to open smartwatch.c. Okay, that was interesting. Am I watching the right one? No, I need to be watching vidlive. Okay, that's embarrassing. There we go. Wrong smartwatch.c. But as you can see there, we got a notification up in the top. Now, the reason we didn't get a whole billion, like you can see here, it printed to standard out a whole billion, is that libnotify actually puts a cap on how many you can send at once. And in my YouTube short I did where I demoed it, I actually put a U-sleep after every notification in Smartwatch so that it didn't bug out libnotify. And that generated a whole bunch. But as you can see here, all of our Smartwatch clients that were connected got a notification because I got them to print to standard out. And we sent a notification to 255. Now, if I kill Rolex Hound, it should clear the subscriptions table. So we'll kill Rolex Hound. As you can see, we clear 256 entries in the subtable because remember, it has to reset Rolex Hound as well. So these guys are not actually watching anything. So if I kill all of them, you can see that it clears 0 entries because those entries have already been removed. So that's it. I really hope you guys liked this video. This is a sick project like thread pools, Epoll, custom network protocols. It's awesome. And you get something really useful at the end of it.